Hello everyone. In this video I'm going to talk about a few important topics and examples regarding scalars, vectors, and beyond that are important for you to know, and I typically basically tease my students in my classes with. So most of the time when somebody asks you what's the difference between a scalar and a vector, you would say the scalar needs only a magnitude while a vector needs also a direction. Well, that is correct, no doubt about it, but there are some other properties and some examples that might challenge this distinction. Like what? For example, one of the first entities that I would like to talk about is electric current, I. So I always ask them, what is electric current? Is that a scalar or a vector? And if they turn out and tell me that it is a scalar, then I ask them, well, doesn't it have a direction? If I have an electric circuit, right, like just let's say a simple DC electric circuit with a battery, with a resistor, and let's say, for example, with an amp meter and something, correct? And that's it, right? Or you can add also a voltmeter. So the question is here, doesn't this current I have a direction? It does. It can go this way or it can go backwards, right? So it does have a direction. It can flow in different direction, and it has a magnitude in amps. So then they turn out and say, well, it is a vector. I said, okay, well, now if something is a vector, it's not just enough to have magnitude and direction. There are some other things that need to hold. And one of them is the addition. Okay, if an entity, a physical entity or quantity you might call, is a vector, the addition of that should follow the addition of vectors, right? For example, if I have a number that is, for example, I have mass 1 that is 3 kilogram, and I have mass 2 that is like 5 kilogram, correct? If I put these two masses together and form a new mass, call it M3, well, clearly M3 is sum of the two numbers, it is 8 kilogram, right? This is addition of scalars. But vectors, if I have a vector of 3 units and a vector of 5 units, the summation is not always 8 units, right? For example, if I have a force in this direction, this force is 3 Newton, F1. And I have a force perpendicular to that. This force F2 has a magnitude of 5 Newton. Now the summation F1 plus F2, if you call it F3, the magnitude of F3 is definitely not 8 Newton in this case. We have to use the parallelogram method or the triangular method to add them, correct? So here you form a parallelogram, which in this case it is also rectangle, and the diagonal of that, if you draw both of them from the same point, this is the magnitude, and clearly the magnitude of this is the square root of 3 squared plus what? 5 squared. So only addition of two vectors has the sum of the additions when the two vectors are on the same line in the same direction. That's the only case. Right? So addition of vectors is different than scalars. And now my question is, what about the electric current? So does electric current follow this addition of vectors? And for that, we use the Kirchhoff's current law, and we say, well, if I have a node, and here two currents are coming, and one current is going out to the node. So I1 is coming in, I2 is going in, and I3 is going out. So consider this node versus now this node, where it is basically the same thing, except that the angle of the wires is different. Correct? Now what? So the question is, what is the relation between I1, 2, and 3, and then my student would say, well, I3 is equal to I1 plus I2 in both cases. And then I say, well, it seems like the angle of this wire, this one versus this one, clearly you see the direction or the angle has changed, and so it seems like it has no effect on the addition, and all you are doing here is adding the magnitudes of amps and getting the equivalent. So it seems like the electric current does not really follow the vector addition, right? I mean, if it was real vector here, if let's say I1 and I2 are equal, then summation here would be 0, while here the summation is definitely not 0, right? Here you have to add I1 and I2 both from the same point, and then you form a parallelogram, and then this is going to be like the addition of them, I3. Well, in this case, even if they were equal, or even if they were not equal, still it is going to be on this vertical line, while here it's kind of like a horizontal if the angles are the same, right? And the magnitudes. So clearly you see that I, the electric current, is a scalar. So what about that basically direction, that it can go one way or the other? Then we can consider it a scalar, but with a sign. If it goes in one way, we might consider it positive. If it goes the other way, we might consider it what? Negative. And you know, scalars can have positive or negative signs. So electric current is a scalar, okay? So this is one of the things that I tease my students. The other thing that I sometimes use in my dynamics class is angular velocity omega. So omega is defined as what? The time derivative of angular position theta. You can say this is the limit of delta theta over delta t when delta t goes to what? To 0. And now I come and ask him this important question. Here, your delta t, you see clearly you have a ratio here. Your denominator delta t is definitely a scalar, right? We know time is a scalar. The question is, what about delta theta? Is this delta theta a scalar or a vector? And they might say it is a vector. It should be if omega, angular velocity, is a vector, and we know it is. So if this guy is a vector, the only solution possible is this delta theta has to be a vector, right? Because you cannot divide a scalar by another scalar and then you end up with a what? With a vector. Right? So the only solution is this delta theta is actually like a what? Like a vector. So I divide a vector by a number or multiply it by inverse of that, which is another number, and I get what? Another vector. And now the question is this delta theta really a vector? Right? And you might say, well, it is. It definitely has magnitude and it definitely has direction, correct? So it might be along x-axis, the change of angle along x, or along y, or along z, rotation along any of them. So it definitely has a direction, it definitely has magnitude, and I say that's right. Now, another thing that two vectors should have is when you add them together, if A is a vector and B is a vector, the order in addition does not matter. So A plus B is the same as what? B plus A, correct? We know the vectors follow what we call the commutative law. Right? If something is a vector, addition of that will follow the commutative law. Now my question is this: if you have a delta theta vector 1 and a delta theta vector 2, if you add them in and then reverse the order of the addition, is the result going to be the same? And to demonstrate that, here I assume that, let's say the first one is a rotation about x, the second one is a rotation about y, and then I reverse it. First do it about y, then do it about x. With so much of angle, it doesn't matter. So let's say one of them 60, one of them 30, or the other way, or 45, or any angle. So the question is, if I rotate an object first by so many degrees along x, followed by so many degrees along y, then I reverse it. First do so many degrees along y, then so many degrees along x. Is the final configuration of that object going to be the same? Let's find out. So here, I show you a demo. And this demo is the same thing that I used previously to show you affine transformations and so on. So here I have a house, simple house in MATLAB, and the house is upright. What I will do is I will first rotate it 60 degrees about the y-axis, and then what? 30 degrees about x-axis, right? And I show the result of that in blue. Then I'm going to what? Reverse the order. So first this A is a rotation matrix. So first I do rotation y followed by x, then I do what? Rotation x followed by y. And I do one of them in blue, the other one in green, right? So here we go, let's run. Well, clearly, as you can see here, the two configurations are completely different, right? 60 y followed by 30x, then 30x followed by 60y. You clearly see the results are absolutely different, and it doesn't matter if I change those angles. Maybe I can make both of them 45. It does not matter. You're gonna see the final configuration to be what? Different, right? Here you can see that, correct? And I can have the original one as well in red, but in this case the goal is to just look at the final ones and see whether they are the same or not, because they both started from the same shape. So clearly you see the answer to this question that I said is they are not. And well, if they are not, then this delta theta cannot really be a vector. So if it's not a vector, delta theta, and it is not, if it's not a vector, how come when you divide a scalar by another scalar, you get a vector, omega? So either omega is not a vector, it is a scalar, or there is something else going on. And the answer is there is something else going on. Okay, omega is a vector, but what's going on here? Well, the matter of fact is that's a limit. What you really need to look at is omega itself is d theta over what? dt, if you want to write it as a simple division without any limits. Now, dt is definitely, again, what? This is a scalar. Omega is a vector. Now, the question is, what about dt? Is this guy a vector or a scalar? And you might say, well, what's the difference between dt and delta t? They seem to be the same thing, right? dt looks like just the limit of delta t when it is very small, correct? So it's a differential term, it's an infinitesimal rotation. This is a non-infinitesimal, right? This is a finite rotation, right? So magnitude of dt is what? Way, way less than 1, which basically means very small. This delta t does not have to be very small. Now the question is, if you make the rotations very, very small, does it follow this thing? In other words, if I say d theta 1 plus d theta 2, is that the same as d theta 2 plus d theta 1? How about this? So if you limit your rotations that we did in that animation to very small angles, not large angles, 30, 40 something, way quite smaller than 1 degree or so, right? A small angle. What would you get? Would this red and the blue house will be on the top of each other or no? So here, instead of 45 degrees, I make it like 2 degrees each, right? Let's just not even less than 1, just 2 degrees. I'm just making them smaller. Look at now. So now if you can see, they are almost on the top of each other, right? You can see that clearly. They are almost what? On the top of each other. Is that really perfect? No. If you zoom in really high enough, you will be able to see some minor differences between the walls. Okay, but it is very small. You have to really zoom in. Okay, so let me see if I can zoom in here. Right, so now you see some small gap between the two walls. Okay, it's just for 2 degrees. Now go ahead and make it what? Less than a degree, 0.2 of a degree. Now see if you can find the gap. They are almost perfectly on the top of each other. And now you need to do a lot of zoom. I'm not sure if I can even show it to you. You need tons of zoom if you can ever to see some gap. So I guess now you begin to see some gaps between them. Right? And this is 0.2. Now because d theta is like a limit, like you're almost going to 0. Now if you make it 0.002, right, go very small, now it is almost maybe impossible in MATLAB to detect any gaps. Okay, so since d theta is a limit term, is an infinitesimal, in this case, the final orientation of the object in both scenarios is going to be at the top of each other. You see, I can barely almost see any gap between them. Right? So in the limit, this equality will hold. So yes, this is correct. And if that's the case, I can say yes, d theta is a vector. And if I divide the vector by a scalar, I will get a vector. So this delta theta thing is an interesting entity. It is an interesting entity. When it's finite, and it's not necessarily small, it doesn't behave perfectly like a vector. But when you make the size of it smaller and make it infinitesimal, now it follows what? All of the requirements for a vector, okay? And that makes omega to be a vector as well. Okay, so we talked about I and omega, and then finally, to make the teasing complete, now I come and ask them, well, what about the moments of inertia that you learn? Or what about the stress? Or what about the strain that you learn, like IXY, sigma YY, correct? Epsilon XX, and so on. What type of entity are these guys? Are they a scalar or a vector? And that is when I hear one group say they are scalars, one group say they are vectors, and I let them debate, and at the end I say, well, the matter of fact, it's neither one. It's not a vector, it is not a scalar, it is, these guys are something beyond a vector. If you look at them, they have 2 subscripts, which means they need 2 directions, okay? For example, if you look at the stress, and if you know from solid mechanics, we have this guy called the stress element, right? So when you look at the stress element, and let's say this direction here is x, then you say that this stress here is what we call sigma xx, and then this stress here, we call it tau xy. Correct? Similarly here, this one you might call sigma yy, and then this stress you might call it tau yx. What does it mean? Well, the first entry, as you know, shows the plane or the normal to the plane. So when it says x, you see both of them have the first entry as x. It means the x-axis here is perpendicular to that plane. The normal to the plane is the x-axis. So for this plane, it is the x-axis that is normal to the plane. For this one, it is what? The y-axis that is normal to the plane, right? And for example, if you have something on this guy here, on this face, the normal to this plane is what? It is the z-axis. Therefore, if I have a normal stress here, you might call it what? Sigma z, and then the second entry that you have shows the direction of that physical quantity. So here it means it is also in the x direction. This means no, it is a shear stress in the y direction, right? So here, for example, if I have a stress like this, it is a shear stress tau because it's tangent to the surface. It is on a surface with normal of z, but the direction of it is y. And if I have something like this, I call it what? Tau z x. And similarly, I can go here and declare this guy to be tau x z. And here I will have what? Tau y z, right? So you need two directions. One is the plane, the other one is the direction of that stress element. So I say when you talk about the stress, right, it is really a matrix of numbers, correct? It is sigma xx, sigma yy, and sigma z. The normal stress is on the diagonal. And then off diagonal elements are what? They are shear stresses like this, correct? Well, of course, in solid mechanics, you show that the matrix is symmetric and these elements mirror image of each other. They are the same. So tau xz and xzx are the same thing. The same thing called yz and zy and xz and zx, or xy and yx, right? So what kind of entity is this? This is what we call a tensor. What is a tensor? A tensor is like a generalized vector. Okay, and to show that how many directions that physical quantity need to specify it, we give it what we call a rank. So if it needs two directions, we say this guy is tensor rank what? 2, which means it needs two directions. In that sense, I can say that a vector like omega that we know is what? It is a vector, but also instead of vector, I can say it is a what? It is a tensor, but it only needs one direction, so we call it a tensor rank what? 1. So all of the vectors that we know, they are all tensor rank 1, and also your I electric current, which is a scalar, it is a what? It is a tensor, but it doesn't need any direction, so it is a what? Tensor rank 0. Okay, so scalars are tensors rank 0, vectors are tensors of rank 1, and then above that, if you need more than one direction, you call them tensor rank 2, 3, so on and so forth. So the tensor rank 2 that we know in mechanical engineering, they are what? They are the moments of inertia, they are the stresses, and they are the strains. And now, as the last bonus thing, somebody might say, well, is there any tensor rank 3, 4, or something like that? Let's just focus on tensor rank 3. Have you seen anything that is a tensor rank 3? And then you probably would look for something that has 3 indices, right? 3 subscripts, because a vector, you would say what? You would say f of x or f of y or something for that matter, correct? So you say, well, this f has only one subscript, force, so it is a tensor rank 1. This sigma has 2 subscripts, so it is a tensor of rank 2. So if I can find something that has 3 subscripts, it could be a tensor rank 3. And then one of the things we have in robotics that has 3 subscripts is called Christoffel symbols of first kind, which we use in dynamics equations of a robot and manipulator. And the definition of this guy is if you write the equation of motion for the ith joint, or ith member, ith joint actually here, as the torque applied to joint I is coming from a mass matrix and then some centrifugal and Coriolis terms, and then the derivatives of the potential energy with respect to the joint variables. So this is the equation of motion that you can apply for each and every one of the joints. Then this term here that is multiplied by these velocity terms, angular velocity or linear velocity terms of the joints, this term, if you look at it, it has three subscripts. This term has I, J, and K, which, as I said, we call it Christoffel symbol of first kind. And what it is, you basically calculate it by taking the partial derivatives of the components of the mass matrix with respect to the joint variables. Okay? And the question might be now, is this a tensor of rank 3? And the answer is no, it is not. So this guy is not a tensor rank 3, although it has 3 indices or subscripts. If you want more explanation on it, refer to this book, Applied Mathematics for Scientists and Engineers by Bruce R., if I'm hopefully pronouncing his name correctly, Kosey or Kosey, and Eric Westwick. Okay, so they mentioned that because the elements of this guy does not follow the transformation that the tensor elements do, so it is not really a tensor rank 3. But I don't want to make this lecture about tensors and general properties of tensors. So just for your knowledge, this is one of the very few things that you see in engineering with 3 indices, and you see that in robotics, and it is not really a tensor rank 3 because it does not have the properties that a tensor should have, although it has 3 indices. Okay, so here I introduced you 4, or here you might say, yeah, if you called all of this the same kind, you can see you're going from scalar to vector to tensor 2 to something that looks like tensor rank 3, but it is not. So hopefully that was some good motivation for you to understand what type of physical quantity is some of those famous ones that you see in your daily studies in mechanical engineering. So thank you so much. I will see you in my next video.